I don't know if that's recording. I kind of don't think that it is. Anybody online? Maybe not. I think I'm going to leave that set up for now. Make that open in a second. Validating my session. All right, so for class today, we're going to talk about 3D printing and some of the limitations and software that's involved with that. If you can, go online to the lesson page for today. This is the wrong class. Wrong class. Then on there, download the STLs for these parts. So there's cube, gaps and bars, inclines and bridges. We're just going to take a look at some of these files inside the Cura program. So once you've got those downloaded, you can go to Apps Anywhere, find Ultimaker Cura. It should be somewhere near the bottom. So QRSTU here. And then launch that. I'm not sure why mine didn't launch. What's that? The inclines and bridges, the gaps and bars, and the cube, the .stl versions. So there's the SolidWorks part versions, and there's also the STL. The STL is just the geometry. In fact, we can open these with the 3D viewer in Windows, and you'll still see the geometry of the parts. We're going to talk about all the different features inside a typical slicer for a 3D printer. And then talk about some feature resolution and some other things that we can use as part of our system. You guys want to come up and take a look at some of these, you can too. I'm going to try and put them on the doc cam so we can all see them, but not sure why. Cura is not opening. I'm going to try launching it from the cloud paging software. It says it's running. Let me minimize these other things and see if it shows up. Authorizing. Well, that's loading. Let's take a look at these. How is this oriented? So this is the first part. I want you to look at that a little more directly down. Trying to look straight into the sides there and have it not terrible. Where's no, that's better. So here we can see that what we have is a series of gaps underneath parts. And then what it does, the gap gets smaller, but the angle on the inclines on the side of the bar get bigger, right? So the amount of overhang that we have is increasing as I go along the length of the bar. And on the bottom, I actually have, can't see it very well, but there's the angle of the inclines on the corresponding face. So we can see that even up to kind of a 45-degree angle, the sides of the walls of the part are pretty clean. And then once we go to 50 degrees and 60 degrees, we start to see a little bit of deformation of the path of the overhang, and then our bridge is not quite clean, right? So there's a little bit of kind of a bumpiness there on the tops of those parts. And so that's the first thing that I want to talk about in terms of the limitations of the software. If we look at in the Cura software, I can agree to the user agreement. I'm just going to hit next and then skip the account. And then I'm going to add a non-network printer. And I'm just going to use the Ultimaker S5. So here on the software, if you look on the other screen, you can see here non-network printer S5 next. And that'll load in all of the kind of client side information it needs to be able to export the code for that printer. And so we have the size of the printer, the build height, volume, all that stuff is already loaded in here. We also have it as a dual material printer, so we can use those options. If I pull up my STL for the gaps and bars, or sorry, it's the inclines and bridges. The way that this part was printed, you're killing me, Apps Anywhere. The way this part was printed was so that way the inclines are at an angle relative to the z-axis, the vertical axis of the part. This should load a little bit faster because it shouldn't give me all those prompts again after I reload it. So hopefully that'll just take a second to load in. There we go. So I'm going to bring in that inclines and bridges file again. And we can see how that part looks inside the geometry. I can rotate this around, use it and position it using the options over here on the right. So I'm going to rotate this up 90 degrees. And that's how this part was printed, right? And I'm just using the middle mouse button to drag this around. And if I want to use the right mouse button, I can kind of rotate around different directions. These red faces right here, those are inclines that are steep enough that the slicer thinks that it should put supports underneath those parts. So when I hit slice on this, what it's doing is it's taking this part and it's dividing it up into layers. And then based off the layers, it draws the tool path. It also identifies any faces or edges that are past a certain threshold, and it can put supports underneath those parts. This is exactly how this current part was printed. And you can see that each of these layers here, especially on this really high incline, the 60 degree, doesn't actually have anything supporting it underneath. So there's a amount of material here that's being extruded that is extruded out past the edge of the previous layer. Generally, as long as you have some amount of overlap between the layers, so the nozzle is not hanging over nothing, you can get a reasonable overhang and still get good quality prints. And then once you get past kind of this point here, right, when we get over here, that's when you want to start having supports underneath the part. Almost all of your slicers have the option to include supports in their options. So this is the basic options for Cura. We can turn the supports on, and then I can re-slice this part. And now you can see it added supports to the part. I don't know how to, is anyone else getting the same error from Apps Anywhere? I'm just gonna try refreshing my apps. Maybe that will do. Did it close out on you? At least it's not just me. This is free software. Not a license problem. It's just the university trying to upset me. So with that support option checked, for all of those faces where the incline was past whatever threshold is set inside the system, it generated material below that surface to support it. And so you get a better quality print. And then on this one that I have the physical part, I just told it not to do that. So you could see what the quality looks like without the supports at those angles. I forgot to turn the supports back on. I work fast because it's going to crash on me again. Right? So you can see there are supports here under the bridge, right? And then the supports actually here are not touching the sidewalls. And the ones over here on the 60, we've actually got support all the way under the wall, kind of all the way down, right? And the machine is automatically deciding kind of where to place those bridges, those supports based off the geometry that I input into the part. And you can have a lot of control over all those features or you can just use a lot of the defaults. In this case, we're using kind of a lot of the default settings, but we have options down here to change a lot of those different things inside these sets, right? So where do you want to change that overhang angle? We can go custom recommended. And I think there's even an option here to change your profile and basically how many different kinds of options do you want to have. So you can go from kind of very, very fine control to having control over every single little thing, but then you have a lot of options, right? So everybody see that? So what I did was I went from here, there's basic, advanced, expert, all. If I go to all, you can see all the different options that are actually included in the software that change the geometry of the supports. And I could change all those things. Most of the time, you come in here to basic and you decide just, do you want supports? And, do you want them to be everywhere, just touching the build plate? A lot of times we just do it touching the build plate because we want to improve the build plate adhesion. We're not really that worried about bridges or holes inside our part. Another thing that I like to use, which is not available in the basic options, I think you go to advanced, it should just give it to us. So you may have to go to expert, is the option to use a tree pattern as opposed to the normal one. The nice thing about the tree is that the supports will come from a common structure and then kind of build outwards and then also expand. So if you have a big flat surface that you need to support, it won't draw supports all the way down. It'll start at kind of a trunk and then branch out to that flat surface to minimize the amount of material used. Not super great for something like this, just because the area being supported is so small. So it's not really necessary. That's a good thing to use. I don't know if I want to pass that around if you want me to look at it. Yeah. Yeah, so it'll solidify faster. Yeah. Yeah. So yeah, one of the things that I want to talk about next is really just the option between infill versus wall thickness. So I'm going to delete this part from my prepare options by deleting it. So click on it, hit delete key. I'm going to bring in this cube. And the only reason I have this cube is for you guys to look and see the difference between print time, infill, and wall thickness. So if I slice this cube using just I'm going to use the normal settings. You can see that inside this part, there's an outer layer, which is 1 line thick. There are 2 inner walls, and then there's an infill. And I can control kind of each of these independently. Really, the outer wall and the inner wall are typically rolled together into one option. So the walls here, I can say how many walls do I want? I can also specify the wall thickness and it'll automatically calculate the number of walls that I get. It's important to know that when you specify the wall thickness, you don't actually get a wall that's that thick. It rounds to the next appropriate value. So if I say I want a wall thickness of 2, it calculates and says, okay, well, you're going to get 7 walls. The reason it does that is I have a 0.4 millimeter diameter nozzle. So a wall is 0.4 millimeters thick by default. And so I'm not going to get exactly the right number all the time. And there's a little bit of overlap between each of them. So it may use 0.3 for some of the inner walls. And it's calculating all that stuff behind the scenes. But you can see that it kind of has to round, right? I also want you guys to look at the difference in the print time and the mass of this part by changing this number. So if I go to a 2 millimeter thick wall, I have 7 wall lines and my print time is 44 minutes and it has a total mass of 6 grams. If I do something different, I'm gonna go back to 1 here. We have a print time of 33 minutes. So it saved us a little bit of time, and our total mass is 5 grams. So it saved us only a small amount of time and a small amount of material to add those additional walls. If I go into my infill, and I say I make this 40%, so I'm doubling the infill. Again, a similar effect. I've got, so doubling the number of walls versus doubling the infill. We've increased the time by about 10 minutes, and I've increased the material by about 1 gram. If I take this to a kind of a logical extreme, if I make this, let's say 90%, I don't really want to use 100% infill. I would never recommend using 100% infill because it usually doesn't give you good quality. It takes you 50 minutes to print this part, and it's 9 grams. If I do the opposite, I make a 0% infill. Still takes 27 minutes. If I make my wall thickness, let's say 20, takes an hour and 20 minutes, right? And is 10 grams instead of 9 grams. What I would recommend that you do is balance the material strength that you need with the number of walls, and then interior support with the amount of infill. So if you have a big volume that just needs to be supported on the inside, use infill. If you need a strong part, use walls, because the walls are going to follow the contours of the part. And so they're going to be able to better distribute the forces for a generic loading condition where the loading is in a direction that you don't know. Whereas the infill will help keep the layer on top of whatever you're building out smooth. So if you have a lot of void on the inside of your part, the infill is going to keep that void from flexing or deforming. And so it's going to keep that rigidity so you don't lose the shape of the object you're trying to print. Physically, you can see we have, this is I guess. This is a 10% infill, 20% infill, 30%, 40%. Actually, I think I'm missing one. I think this is actually 40, 50, and 60% infill. So you see that as I get close to 60%, it's almost getting to the point where it's pretty solid, right? I think all these actually have 3 walls. These parts are pretty strong, right? Having a part like this with 3 walls, I don't need any infill on this part to hold the structure, just because it's not that large of a volume. Even in a part like this part has 2 walls, 2 lines for each wall. So each wall is actually 0.8 millimeters. And I can get pretty good rigidity out of a part like this if I make sure that my lines here, like my width, the height of the wall, is not too long. And I use features inside the part to add some stiffness, right? So you can make pretty reasonable parts that are pretty stiff. I mean, right? And for something like this, where it's not structural, it didn't break or ding or damage or deform or anything. It's just there to keep the components inside it safe. You really don't need very much material. You can see there's some supports on the edge holding up that tab. This one was printed with just, this was on the build plate, which you can tell it's nice and shiny, nice and smooth. It was on that glass build plate. And then I've got some supports on the inside to keep that bottom plate rigid, because otherwise this bottom piece would be kind of flexible and it wouldn't provide rigidity to the rest of the structure. So I'll put these in there. Okay, pass it down. I haven't really mentioned it yet, but we also have this option here for bed adhesion to the bed. And if we scroll down below our infill and support, there's this build plate adhesion. This is one of the, I would say, most important options to consider and adjust based off what you're printing. As you print larger and larger parts, and mostly longer parts, the amount of contraction you get as the part cools becomes more significant. And so the force trying to peel those parts off the build plate becomes stronger. If you're putting a little part, usually it's not going to be an issue. Unless it's a really kind of thin, tall something, then you're going to be in trouble. But if you have a really long, flat piece, you probably want something to help stick that piece down as it's printing. You have a couple different options in here. If you're printing on a rigid glass bed, the brim, which is this first option that you see here, works really well. If you're printing onto a plastic bed, or if you're putting onto tape, because maybe you're using ABS or nylon or something that is much more contractile, it's got a larger thermal expansion coefficient, then you might want to use a raft, which is going to build a structure of the plastic under your part that's a few layers thick, and then build the part on top of that. And that can help because then that structure is also contracting with your part at a more similar rate. So it helps to transition. You don't go straight from having the rigid plate, which is not doing as much expansion and contraction, to your plastic, which is. So it helps to buffer the bottom of the part. Also, the adhesion between a plastic of one type and the same plastic of the same type is typically better than the adhesion between your plastic and your build plate. The only disadvantage of the raft is you're using a lot more material because it's thicker. And sometimes it can be difficult to remove the raft from the final part because it sticks to it so well. The raft itself can also peel up off of the build plate sometimes if it gets big enough. But usually the slicers do a good job of controlling the geometry of the raft such that it doesn't do that. You'll notice that this one actually does not do a solid layer at the bottom. It actually does kind of a, what do you call it, walled structure. And that's so that way the raft itself is not having so much forces in it that it peels up and detaches off of the build plate. Questions on that? Make sense? As Owen was mentioning, you can also go in and change your temperatures for the prints. I have to go into expert for that. So you have your materials, printing temperature based off of that. A lot of the slicers will load the temperatures based off the material that you're printing with, but you can kind of force it to use a different temperature. Most of your plastics are going to have melting temperatures around 200 to 230 degrees Celsius. I don't know, do you use anything higher than that? 250 for ABS or use 250 for PLA? That's really hot. Are you trying to do, 215? That makes much more sense. Yeah. So 210 is pretty common for PLA. Yeah. So the specific manufacturer will have a recommended print temperature. The only thing I worry about that is if there is an offset error in your print head to the actual rated temperature. And so sometimes you might want to adjust your temperature up or down a little bit from what they rate to get better print quality. Yeah, because they have different conduction coefficients, right? So if you have a steel nozzle, you probably have to go a little bit hotter because you're going to lose more temperature, where the brass nozzle is going to transfer temperature faster. And it also depends on the nozzle geometry. So if you have a bigger nozzle, you need to use a higher temperature to get more flow out of that. And even print speeds. So that'll give you different things. I don't have a great example. One of the things that we worry about with the 3D printing is the interlayer adhesion. I can show you with this, but it doesn't show the other case. Yeah, that kind of works. Broke to the way. If I have a part like this is just a spreader bar. This is actually the spreader bar we used last year for applying loads. This is pretty strong because all the fibers, really the print layers, are going in the same direction. And so when I bend it, the forces on the top and the bottom are in tension and compression. And the forces kind of going in this direction, right, are very, very small. So the the parts when they come out of the printer are typically very anisotropic. Their strength characteristics are very much a function of the direction of the print. If I were to take, let's take this next part, the gaps and bars. Or sorry, yeah, that one. And try and print it up on its side like this, I would get a very weak part because all of these layers from top to bottom would not have the tensile strength that it would have if I printed it flat. Because you think about all the fibers being horizontal, they're not going to hold the force as well. Now, there are things you can do with controlling the temperature and the layer height to improve the interlayer adhesion, but typically at the cost of print time. So if I use a slower print speed with smaller layers, I can usually get better interlayer adhesion. It's never really going to be as good as it is in all directions. But again, then you're taking a lot longer to print. So you can tune those things, but it's hard to get it perfect. And generally, there's a loading condition that you can consider for your parts, and you can orient them in a way that most of the load will be distributed appropriately inside the part. This part itself actually has different size gaps and bars on it. And you can see that if I make a line that is too thin, this one is 0.1 millimeters, 0.2, 0.3, 0.4. Remember, I have a 0.4 millimeter nozzle, and the 0.4 millimeter one has a single wall. And I can see down here, as I go to 0.5, it actually is doing a double wall. They're just overlapped. Then same thing, 0.6, 0.7. Then at 0.8, I actually have the two walls, and I have a little bit of an infill in between those two. And then the 0.9 and then the 1 as we go down through it, right? But keep in mind, just because you have the geometry there doesn't necessarily mean that it'll print. And inside my example piece here, you can see that kind of the same thing on the holes. I can't really see the holes even for the 0.4, right? I don't really see that gap in the part until I get down to the 0.5. And so the variation in kind of the sidewall of that part is bleeding into those pieces. And if I were to take a caliper and measure the width of this last tab, one, you can see that it's not consistent because it actually moved around a little bit. It peeled off the build plate. I don't know if you guys can see the fact that that last little bit is kind of loose and blobby. But it's not going to be exactly the 0.4. It's going to be 0.4 plus or minus something along the length. Same thing for the 0.5, the 0.6. It's going to change as I go down. Then as I get bigger, it might stabilize a little bit. We're always going to have some geometric error in the printer as a result of going through that. So. That make sense? Cool. So I guess the long and the short of that is you got to think about the direction of the geometry of the parts, what kind of wall spacing and infill you want to use, what kind of support you want to use, and any other details you want to try and adjust based off temperature and resolution for the print. I can go through here and change this to extra fine and reslice it, and we're going to get a thinner layer in the Z direction, but that doesn't change the fact that we're missing these first 3 bars, because that is only talking about our height in the Z. We don't have the ability to actively change the nozzle diameter to change the width of each of the lines, right? So we can get a little bit better print quality in that direction. You can go through and change the nozzle size, and I can change the nozzle size on here as well. I'll just change my line width. You see now I have that 0.3, and I can I can even change the line width without changing the nozzle because it's going to change the flow rate, but you're not going to get as consistent a quality of a wall. So really you shouldn't change the length, the width of the lines without also changing the nozzle diameter inside the machine. And if you go really, really small, the machine's going to have a really hard time pushing plastic through. And so your print speed is going to have to be either really slow or you're going to break the machine, or not break the machine, at least, you know, ruin your roll of filament. You're going to have issues printing that out. The same is true for the opposite direction. There's a limit to how much plastic the machine can melt and push through itself. And so if I try and do really, really thick layers, you're going to have issues on that standpoint. So there are bounds as to how fast and how slow you can effectively print things. Yeah, definitely. So the total print time will not change super significantly based off of just a material change, but the settings that you use when printing are likely to change based off of the material. And then those changes in settings will affect the print time. Usually the biggest change from going from one material to another is the printing temperature. And whether or not you need to use supports and build plate adhesion. So PLA is pretty nice because it doesn't contract too much as it cools and melts at a fairly low temperature. It also has a very plastic transition. So it has a range of temperatures where it goes from being solid to squishy to squishier to squishier to squishier to squishier to fluid, as opposed to going from solid to fluid at a single temperature. And so it's less susceptible to small variations in temperature as you're changing because the viscosity is less temperature dependent, right, than some of the other plastics. ABS is pretty good. It's a little bit stiffer than PLA. So if you want to make a part that's rigid, then that's beneficial. It does contract more than PLA does. So you're going to have more issues with not adhering to the build plate with ABS than you would with PLA generally. Now, if you have a heated bed, which is we do on the Gus one, then that's less of an issue because since the bed is hot, the temperature gradient is not as significant from the bottom of the part to the top of the part, but you're still going to have some issues, right? And if you want to move to something like nylon, nylon has a very significant temperature deviation. It's also quite soft. And so it tends to get gummed up in the mechanism itself, and it has a higher melting temperature. So you have a higher temperature on the hot end, larger temperature gradients, more contraction, as well as a squishier material, which means that between where you're applying force to the filament to where it's being extruded, there's going to be more deformation inside that component, right? And so that makes it a little bit more difficult to print. But they're always coming up with new ways of adding additives to the plastics. So there's plastics that have carbon fiber filling inside them, and different things like that that can improve their strength. And then you can also talk about resin printing and those kind of things, which use a very similar technique, except for instead of printing from the bottom up, they kind of pull the parts out of the resin, moving the crosshead upwards as opposed to the build plate downwards, right? But it's very similar. And the slicers that they use are very similar to this as well. So if you get comfortable using one of these softwares, it's pretty easy to transition from one software to another. They just put the options in a different spot, right? So if you wanted to use the MakerBot as opposed to Ultimaker, they have their own slicer. But if you know what the options are, you can typically find the same set across different platforms. Make sense? All right. I want to take a little bit of a look at what these files are outputting. So whichever file you have open, save that to disk. So I'm going to save this just to my desktop. And it's going to say save to wherever. I'm going to open that folder. This is one of the files you're going to submit for the submission for the league. The next file is actually going to be a file that you make using MATLAB and not a slicer. And I'm going to make the video to help you guys walk through that. But what I want to do is actually want to open this with a notepad. So if you, I probably should do that a little bit slower. Oh, it's in binary. I'm going to change the options on this. Settings, printers. Let's do Marlin. Let me just try this real quick and make sure it's giving me the code that I want. I'm going to save this as G code. There you go. All right, so go into printer, do manage printers, machine settings. And what I'm doing is I'm changing the G code flavor from Ultimaker 2 to Marlin. And I'm going to hit close. This won't work on this printer anymore, but it'll allow us to use a non-binary G code that will be human readable. And then when we do save to disk, we can change the format of the output to .G code as opposed to Ultimaker format package. Marlin. So again, in machine settings, printer, G code flavor, Marlin. I'm just using Marlin because I have a reference for Marlin up on the Canvas page. So that's the one that we're going to use. And then save to disk, change it to .G code, hit save. It says, do you want to, I mean, I already have it out there, so I'm just going to overwrite it. And then when you open that G code file with your notepad, you should see the machine code that actually gets sent out to the printer. Now, I can compare this to the notepad version. This one is in binary, which is why it's not human readable. It's just translating the ones and zeros that it would send to the machine into whatever the equivalent character is, which is garbage, because that's not how it's being translated inside the machine. But this version here, the G code it's using actually is human readable. And you can see that anything after a semicolon is a comment. It's just having some information about the system. And then everything after this last comment are commands that are being sent to the machine. So I can search these commands in the reference code for Marlin. Let me go to our lesson page here. And I can look for M140. Let me do Control F, look for M140. And you can see that's a command that sets the bed temperature. And so this line of code is setting the bed temperature to 60 degrees, right? And I can look at 105. And I said that 105 is reporting the temperatures. Again, it's saying it's waiting for the temperature probably to get to that temperature that I set it to. And you can see there's more comments here for layer count, layer 0. And then most of the code is actually this G1 with an XYZ position and an extrusion value. And if I scroll down, you can see most of those lines of code are just positions. And this is what the machine actually is reading, regardless of what flavor you're using. It's saying, okay, go to this position, extrude this much. Go to this position, extrude this much. Go to this position, extrude this much. And all the slicer is doing is it's taking your geometry, cutting it into layers, using that to find vertices, and then linking those vertices together in the code. So it'll go through and, if it starts here, which the start is usually this white spot, right? It's going to go to here and then go to here and then go across to here and then back down and over. And then it's going to draw an arc and then it's going to come down, over, And there's commands for drawing a circle or an arc as well as a straight line. So you don't have to do like little arc, little piece, little piece, little piece. It doesn't have to segment the arc. You can just draw a curve with a certain radius. And you'll do that and go through the whole print. All right. And you can see that even if I zoom in, these arcs don't get segmented going through it, which is nice. The ones on the 9 does, because that's not a circle. You can see the actual kind of transitions between straight line, straight line, straight line. Whereas the one over here, you can't see those transitions because it actually is quarter circle on this arc, as opposed to being a more arbitrary geometry on the 9 and the 0. But there's nothing magical about this, right? Like it's just, go to a new position, extrude a certain amount, go to a new position, extrude a certain amount. And I think hopefully you guys can see that if I knew the geometry of the part, you could by hand write out the code you needed to print that part. And, I think if you go back historically to CNC machining, this is a transition from manual to CNC to layers upon CNC machining. So this is computer numeric control of the extruder on the printer with an extra layer of extraction on the top, which is the slicer, which allows us to just say, hey, here's the geometry I want. You figure out the movements you need to do to reproduce that geometry based off all the different settings that I put in, right? And since Cura is an open source platform, whenever someone wants a new feature inside the software, if they add that, well, then now everyone else has access to that feature. And so it becomes a very feature-rich environment where you have lots and lots and lots of different options, which is why they have the option to hide most of those options, right? That makes sense? Any other questions on that? All right, so what we're gonna do is I'm gonna make a video on Wednesday or Tuesday, but I'll post it for you guys to start working on Wednesday, asking you all to write a simple code in MATLAB that generates some G code for a 3D printer. And you guys can submit that. That'll be your submissions for this week. You continue working on your bridge projects. We'll have the submission for that be at the end of next week, but we won't do the testing until the week after. So you can do a submission sometime next week or the week after, or sometime next week. We can print it and then you can resubmit before Friday of this week after next to use for your final test. And then next week, we're going to talk a little bit about CNC control of milling machines for reductive processing, which uses a very similar architecture to this, but you got to be a little bit more worried about the fact that since you have a drill or a mill or whatever moving around, that you're not trying to make a feature that's smaller than the size of the bit that you're using, as well as you're not hitting things on accident as you're moving that piece around, right? So there's a little bit of extra kind of layers on top of that. But it's not really that dissimilar from what we have inside this slicer right here, just controlling a reductive processing element as opposed to an additive processing element. All good? All right. I'll see you guys in class on Wednesday next week. If you have questions or concerns, or if you want to print your bridges sometime this week, let me know. And I'll be here probably tomorrow trying to get stuff ready for being gone. If not, stay safe. Is that? We're still not going to have class on Monday, not in person, but I'll have that virtual lesson. So if you don't do that on Wednesday or Friday this week, then you can do it on Monday. Okay. Okay. Thanks for coming, everybody. If you guys want to see my bridge that failed from last year, I have it in the box. This is the one that I built last year. Yeah. And Yeah, so it supports the load just fine. The only problem is that it buckles. So if I push down like this, it buckles that way. But none of it breaks, it just falls apart. But it had some supports to keep that from collapsing. Always pretty easy to purchase stuff. Well, so you can load here or here. I actually loaded down on top. If you load at the bottom, then it tries to open it up. Yeah. And then it means it's even worse that way. Now it's like force buckling, right?
So really, it's just.
How much do you want?
Yeah, but I was thinking like a bridge, like so it would have like two symmetrical.
So if you want more lateral stability, then there's nothing wrong. Right?
What if you make like a two? Like, I remember we did it in like
Vietnam.
yeah, where like we were trying to see like.
The only problem with the tube is that since you're loading it like on the top of it, you're going to have a very uneven distribution of stresses because all the load is going to be basically on a point, right? And so you got to worry about how do I load that tube. If it was just it carrying the moment, it would be great. But because it's not a distributed even load like it would be in the simulation, it doesn't work out as well, right? You can try it. If you're going to geometry, you think looks good. Use that for your first print. Yeah.
You learn how to get a.
Yeah. The sketch picture tool.
Yeah.
We're talking about?
So that's a sketch.
Yeah, so to make a sketch. Yeah, just as an example. No, just a sketch like on plane, it's like a starter sketch. Sure. Sketch picture. Pick the picture you want, and it'll bring it into the sketch. And you want to scale it and make it the right size, good. And then you can use that.
Okay.
Does that make sense?
Another question.
Mm-hmm.
So,
The valve?
the valve.
Yeah.
The cylinder. So, we're trying to figure out ways in order for us to like be able to, for them to, you know,